All right. So I'm going to talk about the universe of galaxies, but since the James Webb Telescope has been in the public eye and been in the news a lot, I'll show you some images from that. And some Los Altos High School students have been participating over the years in some of the STEM or STEAM research programs we run at the University of California, Santa Cruz. I actually live a stone's throw away from the school. You'd have to have a strong arm for it to literally be a stone's throw. But I live very, very close to here. I use your tennis courts from time to time. But I work at UC Santa Cruz. I've worked there for the better part of 3 decades. I've been there since 1994, so 28 years. And about 7 years ago, I spent a sabbatical at Google's headquarters in Mountain View. And what they did for me was help me scale up some of these STEM research opportunities, this thing that's labeled Creating Equity in STEAM, or CREST. Google has helped me a lot with that. So I'm first going to talk about some of my research on galaxies. That's illustrated by Hubble and James Webb images. There's some movies in there. And then I'll say a little bit about how you as a high school student can get involved in some of this. And I mean involvement at a variety of levels. You can watch science happen. That's sort of very limited and passive role. But you can also get more actively involved in the research itself over the summer. All right. So, I work on galaxies, and what I'm about to show you is a time lapse of our Milky Way galaxy. And you can see the Milky Way galaxy sort of as a band of light and a little bit of band of light and patches of darkness, clouds of gas and dust, across the bottom there. And this is not a single shot. It's actually a time lapse taken by my friend John Rockman, a physics teacher at Castellea School. So I'm going to remove the label. You can see what this looks like. So you're seeing the apparent sweeping of the Milky Way across the sky. I say apparent because it's, of course, because of the Earth's rotation that the sky appears to rotate in equal and opposite sense. You see, I'll play this one more time, but you can see lightning and shooting stars. You can see clouds going by. There's the tree in the lower right and the lower left that's fluttering in the breeze. Initially, the lights are on. You can see the tree. But the sky gets darker as we approach sunset and as we go past sunset, and someone turns off the light so you can't see the tree anymore. But this is our grand home, the Milky Way galaxy. This is what I do research in. It's one of the most photogenic things you can do research on. It's our own Milky Way galaxy. And it doesn't take much to see it. You just have to get away from city lights to see it. So this is John Rockman's video. I want to show you another video of the Milky Way. Again, you see the Milky Way as a vertical band of light, but also dark patches of clouds of gas and dust. And this time, it's a time-lapse movie of the Milky Way taken by Arya Nirenberg. But what Arya did was, as the sky appeared to rotate because of the Earth's rotation, he kept the camera fixed onto the sky. So because the sky appears to rotate, your camera has to rotate in order to do that. So if I remove the label, you can see what happens. You can't help but notice that we live on a planet that is spinning 24 hours, once every 24 hours. You can see planes flying overhead, but you really cannot help but notice the rotation of the Earth. The sky frame is fixed here because of the way the camera is compensating for the Earth's rotation. But you can see the rotation of the Earth here. I love this video. All right, moving on. Here's the Milky Way again as a vertical band. This is taken in the southern skies. This is a picture of the Southern Cross. In fact, I'll point out the Southern Cross to you. These 4 stars, sort of diamond shape, is the Southern Cross, not far from where the Earth's south pole is pointed, just like the North Pole points towards the pole star. And I want you to focus your attention on this red square at the bottom. No, maybe I'll use my laser pointer. This red square is something called the Carina Nebula. And I'll go back and forth. Oops, sorry. Doesn't, no, seems to go one way. Let me see. Okay, so there's the red square, that's the Carina Nebula. And this is a picture taken by Kiko Fairbairn. It's a ground-based image. And if I zoom in to that square, you can see a lot more detail. And this is a picture taken by Harold Boren. And in the upper right, you see a section of the nebula again. And we're going to zoom into that. And you see even more detail. This time, this is a picture taken with a spectacular telescope located in Chile at the European Southern Observatory. But it's a ground-based photo. And astronomers have wonderfully romantic names for these nebulae. This one is called NGC 3324. And we're next going to zoom into this red rectangle. And you'll see a rotated version of the rectangle. Okay, so not sort of at this jaunty angle, but horizontal. And you'll see three versions of the patch of sky that's represented by that rectangle. Three versions. At the top, the picture taken from that telescope in Chile, one of the best ground-based telescopes. In the middle, picture taken with Hubble. And at the bottom, the picture taken with the James Webb Telescope. This has been called cosmic cliffs because you can see what looks like a sharp edge to this cloud, like a cliff. But it's really dramatic to see the extra stars and the extra level of detail that James Webb gives you compared to Hubble, and what Hubble gives you compared to the best images from the ground. Now, in the next zoom, I'm going to zoom in on that thing that looks like a thumb. That's a little piece of this cloud of gas and dust. I say little piece, but it's bigger than our solar system. In fact, there is a star and planets forming within that little thumb-shaped feature. So let's zoom in on that. And again, you can see the insane level of detail. Just see the extra stars that you can see in that lowest image with James Webb compared to Hubble or from the ground. If you're wondering why are people making such a big fuss about James Webb, these are examples of why. I'll show you some more images from Webb in a moment. So I study clouds of gas and dust in the Milky Way. I study them in other galaxies as well. And I also study stars. And this is a family of stars, a star cluster. Again, it has this beautiful name of Messier 3, M3. And the kind of stars I'm interested in are called RR Lyrae. And if I point my laser pointer to this star over here, you'll notice that in this time lapse, it's not steady in brightness. It's going up and down in brightness. These are a special class of stars called RR Lyrae. They were first discovered because there was a particular star that did this. So all stars of this category are named after the prototype. You'll notice that they don't all pulse exactly in phase. One might be getting brighter while another one is getting fainter. But these are really important stars because they can be told apart from the other stars because of this characteristic sort of heartbeat-shaped pulsation. They go up in brightness, come back down, go up in brightness. They're the heartbeats of our Milky Way galaxy. It's very easy to measure the distances to these stars, unlike other stars in the universe. These are easy to measure distances to. So my students and I have been using them to map our Milky Way galaxy. And when I say Milky Way galaxy, I mean this is an artist's view. We don't have a long enough selfie stick to take a good picture of the Milky Way. Our Milky Way is 100,000 light years across. This bright disk is about 100,000 light years in diameter. So you need a very long selfie stick to take a picture of this. So that's why this is an artist's impression. And our own solar system and sun are located about halfway from the center to the edge of the disk of the Milky Way, about 25,000 light years from the center of our Milky Way to the sun. And needless to say, the sun is not shown to scale, and our sun doesn't actually look like that, okay, in case you're wondering. Now I'm going to remove them and put our galaxy edge on and shrink it so I can show you to scale how far away from our sun and center of the Milky Way we've found stars in the Milky Way. These are, every dot is an RL Lyra that one of my PhD students has found, and they extend 1,000,000 light years from the center of our galaxy. So we are redefining the size of our own galaxy. And it's about 40 times. These stars are located about 40 times further away than the distance of our solar system from the center of the Milky Way. All right. This is the work of Yuting Feng, who's a PhD student at UC Santa Cruz, and a former PhD student of mine, Emily Cunningham, who's a postdoctoral fellow at Columbia University in New York City. We're continuing work on this. I'm going out to Hawaii in November. I just came back from Hawaii to use the telescopes there, where we try to measure how fast these stars are moving away or towards us, because that tells us something about the dark matter content of our Milky Way. All right. On to another galaxy. This is one of my favorite galaxies. This is the Andromeda galaxy. And what you're seeing here are 4 versions of a digital mosaic. On the left is that mosaic shown at low contrast, where you can see the center of the galaxy, and you can see, in fact, you can see a companion galaxy right there. I'm going to point my laser pointer to it as well. This galaxy, oops, it's going way ahead of me. Sorry about that. Press the... I'm talking about this galaxy. If you can see my cursor, can you? No. There we go. Okay, this galaxy over here is something I was studying 3 weeks ago. I was in Hawaii for 2 weeks. We were studying, and I'll show you some details of that. Okay, so this is a digital mosaic. It was the first digital mosaic at that time of Andromeda. It was put together by 2 of my students, Andreas Berlind and Phil Choi. Shomok, Raj Chaudhary, and I took the images originally from a telescope in Tucson, near Tucson, at Kitt Peak Observatory, south of Tucson. And we used it to study how Andromeda is cannibalizing some of its smaller companions. You can see those 2 companions quite clearly here. One is at 12 o'clock, one is at sort of 5 o'clock. You can think of 12 o'clock as lunch, 5 o'clock as early dinner, because that's exactly what Andromeda is doing to these 2 galaxies, right? It's eating them. We use the Keck telescopes in Hawaii that are just coming into view. This is a glorious Mauna Kea sunset, imaged by Laurie Hatch. And those 2 telescopes, each of those telescopes, the size of the mirror is about equal to the central seating area of this auditorium. It's about 10 meters across. It's not a single mirror. It's a segmented mirror with 36 segments. Each segment is taller than a normal-sized human being. This is a beautiful image that came to my attention. This is one of the satellite galaxies of the Milky Way, imaged with the James Webb Telescope. This galaxy is called WLM. I don't know why. It's an odd name for it. But the people who are watching this, the 6 people who are looking at this image, are actually inside a planetarium, and this James Webb image is being projected onto the planetarium dome. The comment from one of them was they felt like they were inside the galaxy. Spectacular detail from James Webb. One of the ways you recognize James Webb images is you notice that every bright star has this 6-pointed pattern around it, because the James Webb mirror segments are hexagonal in shape. So that's a diffraction pattern from the segments. More on Andromeda. And if you look at that crime scene outline on the left, that's the section of Andromeda that we've imaged with the Hubble telescope. And this is the full moon shown to scale. So if you look out today, you'll see something that's just past the first quarter moon. The full moon's diameter is quite a bit smaller than the Andromeda galaxy. But you can't see the Andromeda galaxy with your naked eye at such detail because it has low contrast, unlike the full moon. Now, with Hubble, we can see a lot, and I'm going to show you Andromeda in a great deal of detail. So we're going to zoom in to Hubble's image mosaic. Remember I told you we took this image mosaic 30 years ago. That was 57 images stitched together. Hubble, I've been involved with the Hubble team to take a digital mosaic that has 3,000 images stitched together. You're about to see the details of that. Before we go there, This big arc going across the image, this giant arc going across the image is, of course, our Milky Way. And there's Andromeda. Andromeda is 2.5 million light years away. Let me play the movie, and you'll see. We're going to zoom in towards Andromeda, so you'll see a lot more detail. You can actually see one of the companions of Andromeda just to its upper right. I'm sorry, it's a little choppy in this transmission. Okay, there's one of the companions. There's another companion. We're going to keep zooming. Now, this is not something made up. What we are zooming into is an actual image of Andromeda taken with the Hubble Space Telescope. So you can see individual stars. You can measure their colors. The color is representative of temperature. You can measure their brightnesses. You can even see these dark patches that are in the upper left of this image where gas and dust are blocking the lighter stars. So we use these images for our research. We take spectra for our research. Here is a section of Andromeda where the graph on the right shows brightness on the y-axis and temperature, an inverted temperature scale, so temperature increasing to the left on the x-axis. And we are getting ready to take spectra with the James Webb Telescope, and we should be able to use that to measure the chemical composition of stars, which is something our group studies in great detail. When I was out at Hawaii last month, we were taking spectra of stars through those light purple metal plates that capture the light of specific stars in Andromeda. There's Andromeda in the background. Its center is in the upper left there. This is an ultraviolet image of Andromeda. There's its center. This is its ring of fire, a disk of star formation. And there is the little galaxy M32 that we were focusing on. This Japanese fan pattern is designed to study M32, the companion of Andromeda. All right, moving on. One of the reasons we study galaxies is we want to understand how they collide with each other. A galaxy collision takes a long time. It takes a few billion years. So even though I look old, I haven't been able to see one of these take place in its entirety. Okay, so what we're going to do instead is show you an example of a computer simulation of what happens when two galaxies collide. And we're going to compare them to actual snapshots of galaxy pairs that are at different stages of the collision process. So I'll remove the label and play the movie for you. Okay. As these two galaxies come together, right before they start intersecting, we stop the computer simulation. And here are two real galaxies that are about to collide. If we go back to the computer simulation, their mutual gravity brings them closer together. And at this point, they're actually intersecting. One galaxy is occupying the space of the other. And you can see that if we stop the computer simulation and change our perspective, you can see from all angles they're intersecting. We stop the computer simulation. These are two real galaxies that are intersecting. We go back to the computer simulation, and each galaxy's differential gravity, gravity is a distance-dependent force, differential gravity stretches out the other. And here is a real pair of galaxies that are being stretched out. Each galaxy is stretching out the other. Go back to the computer simulation. The main bodies start to fall back together. And right before they do, we stop the computer simulation. Right there, change our perspective. And here is a real pair of galaxies that are in the late stages of a collision. The main bodies now start to merge back to the computer simulation. And when the main bodies have sort of merged, we stop the simulation one last time, change our perspective one last time, and here is a real pair of galaxies going through the collision process. So galaxy collisions are beautiful. They're wonderful to study. And here's a James Webb image. Actually, the middle and right images are from James Webb. The left image is from Hubble. HST stands for Hubble Space Telescope. And these are 5 galaxies. 2 of them are very close together. Those are these 2 over here. You can see them as distinct galaxies. You can see them here. This is called Stephan's quintet. In the right image, James Webb has imaged 4 of those 5 galaxies, not the lower one. And you get spectacular detail. For example, the top galaxy has this bright source at its center that we didn't know about until James Webb took images with MIRI. MIRI stands for mid-infrared imager. In the middle part of the infrared, that light is very bright from the center of that galaxy. So this is a galaxy system in the process of colliding. If you think galaxy collisions are fun and it's going to happen to somebody else, you're wrong. We're going to be part of a galaxy collision. But I don't see anyone panicking and running out of the room because, for one thing, it's a long ways away. It's 7 billion years away. For another reason, you're not running away is there's no place to hide. Okay? And when it happens, it's going to happen to all of us. There is, we discovered our group at Santa Cruz in 2005, so now 17 years ago. We discovered that the Andromeda galaxy that you see as this little blip in the upper left there, we discovered that it's 5 times bigger than people previously thought it was. 5 times bigger. Instead of being something like 200 light years in diameter, in radius, we found that it's 1 million light years in radius. Right? So 5 times bigger. So you find out your neighbor is 5 times bigger than you thought they were. It's scary. In 2012, 7 years later, so 10 years ago, a group led by Roland Vandermarel in Baltimore, we were part of that group of researchers, we discovered that the same galaxy that's 5 times bigger, we found it was 5 times bigger, and now we find it's heading straight for us. Okay, so 2 bad things about your neighbor. They're bigger than you thought they were, and they're coming straight for you. So this discovery was made, the second discovery of how Andromeda is moving, was made using the Hubble telescope. So NASA made this publicity video. I don't know if you call it a publicity video when you make a doomsday video like this, but anyway, I'm going to call it that. They made this video that you're about to see that shows the future Milky Way Andromeda galactic collision. So I'll remove the label. This is how the sky looks today. You know, there's the Milky Way as a near vertical band. There's Andromeda right there. And astronomers wondered why Andromeda was getting bigger and bigger, and then it hit us, okay? Oops, let me go back to this. So this is today. This is how it's going to look 2 billion years in the future, much bigger. And 3 to 4 billion years from now, there'll be a spectacular collision between the Milky Way and Andromeda. There'll be lots of new stars formed during that time. So there'll be fireworks in the sky, permanent fireworks, not the 4th of July kind. We probably will stop celebrating 4th of July because we'll be dead at this point. I don't just mean you and me, but I mean human species as the human beings as a species, unless we move out to another moon or planet in the solar system, outward. We better not move inwards because what's going to kill us, I mean, we might be killed by politicians well before that. Okay? I'm not going to put that past them. Okay? The way things are going on in Ukraine and Russia, who knows, right? So if we manage to survive politicians, we still have to survive disease. We have to survive our killing of the environment. If we manage to do all of those things, we'll live long enough to see the sun engulf the earth, okay? So it'll all be in vain. You know, you live a healthy life, you live for 5 billion years, only to get swallowed by the sun. So instead of waiting to get swallowed by the sun, what you should do during those 5 billion years, and this is to you, because I haven't lived a healthy life, so I'm not going to live for 5 billion years, you may. What you should do during that time is build a rocket that carries you outward in the solar system to one of the moons of Jupiter or Saturn, because then you can watch. Mars is a bit too close for comfort, because when the sun bloats up and becomes a red giant and swallows the Earth, Mars is going to get really hot, okay? So you're worried about global warming now? That'll look like a walk in the park. So go out to one of the moons of Saturn or Jupiter, and if you're wondering what to build the rockets with, I have an idea. The people who made this movie, this NASA movie, they know something about these rocks in the picture, because you'll notice in 7 billion years they haven't weathered. So they must be very durable rocks, so you can build your rockets out of these rocks. Go talk to the NASA folks, they'll tell you what these rocks are made of. Actually, that was a silly mistake in the video. They should have weathered the rocks. All right, I'm not going to stop at this galaxy. This is one of the biggest galaxies in our neighborhood, but the reason I'm showing it is at its center, there is a supermassive black hole that was imaged recently with the Event Horizon Telescope. This is the most photogenic black hole you'll ever come across. The galaxy it's sitting at the center of is called Messier 87. This is light bending around the black hole because black holes and anything with mass bends light. And so you're seeing a silhouette of the black hole. It's radio waves from behind the black hole being bent by the gravity of the black hole. This was imaged with fair to say, the Earth's largest radio telescope, because it wasn't a single telescope, it's an array of telescopes located throughout the Earth that worked together to produce this image. Right. Now, here's another example of light bending. This is an image taken with James Webb. This phenomenon is called gravitational lensing. And if you look closely, you'll see that there are these spectacular arcs. These are background galaxies whose light has been distorted by the gravity of these foreground galaxies. Okay? So James Webb took this picture, and I want to show you that these two pieces that I'm going to highlight, these two pieces that are highlighted by the rectangles right there and there, are actually images of the same background galaxy. They have exactly the same spectrum. They have hydrogen and oxygen in the same ratio at the same redshift. Because of the expansion of the universe, redshift tells us how far away the galaxy is. Those two pieces are actually a mirage of the same galaxy. Now, gravitational lensing is nothing but a cosmic telescope. So we can line up our telescopes, like James Webb, behind this telescope and use the combined power to study some of the most distant galaxies in the universe. And that's what's shown in this slide. I love this image. Whoever decided to take a Van Gogh image, Starry, Starry Night, and put that together with the James Webb image was just genius. I wanted to show you this. And, why I study galaxies is as follows. I want to take 1 minute to explain that, and then I know we're at our nominal time, so tell me if I should be stopping right now or if I can go on a bit longer. Please tell me who is keeping time here. Keep going? Okay, thank you. So I'll go for another 5. Okay, so I wanted to come a full circle and talk about why I study galaxies. The image you're seeing here is nothing other than the afterglow from the Big Bang. This is an image taken with a space-based telescope. It's a microwave telescope, detects microwave radiation, from the afterglow from the universe. What I mean by afterglow is if you have your oven turned on and you're cooking something, when you turn off your oven, it doesn't instantly cool to room temperature. It takes a while to cool down. Our universe has been cooling for 13.7 billion years after the Big Bang, but it hasn't cooled completely to absolute zero. It's at 2.7 degrees above absolute zero. You all know what absolute zero is, minus 273 Celsius. And 2.73 Kelvin is high enough a temperature that you can measure radiation from the universe. That's what this image is. You'll notice it's not smooth. There are pockets of the universe that are higher temperature than other pockets. So the dark areas are lower temperature. The yellowish orange are high temperature. There are fluctuations in the universe that's caused by, can you guess what? Quantum mechanics. So quantum uncertainty in the early universe is reflected in this patchiness that you see here. This is not a measurement error. It's not that our telescope wasn't good enough. These are real fluctuations in the universe. So one of these upward fluctuations is actually an upward fluctuation in density, and gravity, just like happens in human society, gravity makes the rich richer and the poor poorer. So if there is something that's already higher density than average, it turns into a small galaxy. Those pieces then interact, cannibalize one another to form a big galaxy. Within that, there are stars that go through chemical evolution. Some of them explode, and it's in the interiors of stars and in their explosion that all of the elements in the periodic table, other than hydrogen and helium, are produced. So you and I are sitting here today because we're made of elements produced in these explosions. So there's our star and planet. There are wonderful molecules, protein molecules, and wonderful living things that come out of these molecules. So I'll stop here, and I'll take questions about how you can get involved in this research. Thank you.